Okay, we've built up our intuition about pairs of random variables in the discrete case. Let's carry that intuition over to the continuous case. So remember, in the continuous case, we have to start with the CDF. In this case, we have a joint CDF, which is the probability that x is less than or equal to some value little x, and y is simultaneously less than or equal to some value little y. And we're going to have to also replace all of the sums we saw in the discrete case with integrals. Okay, so we'll say that a pair of random variables, x and y, that they're jointly continuous if they have a joint CDF, this function above, that is continuous, meaning that it has no discontinuities or abrupt changes, and it's also differentiable almost everywhere. So almost everywhere we look, we find a derivative. And then we can define this joint probability density function, or the PDF, f of x, y. Now we have a little f, and that for a pair of jointly continuous random variables is simply the second order partial derivative with respect to x and y of the joint CDF. Okay, so it's the same idea that we saw in the single continuous variable case, which is we take the CDF and we take its derivative. The only change is that here, since we have two variables, we take a partial derivative with respect to x and then a partial derivative with respect to y. And where those derivatives don't exist, it's okay to put any value, and we kind of saw that that doesn't really cause us any trouble. It's just where we have something like the uniform PDF and it kind of jumps up, we can, at that exact point of that jump, we can put any value. That's really where this matters. Okay, the range Rxy of a pair of jointly continuous random variables is just what you would expect it to be. It's the set of values where the joint PDF is greater than 0, so where it actually has positive values. Okay, so that's basically where the random variables are allowed to lie. Okay, so we have the usual properties, so we're going to look at how those appear in the form of the joint PDF. So it can't be negative, so it's always greater than or equal to 0. If I integrate it across x and y for the full range minus infinity to infinity, I'll get 1. So it normalizes to 1. If I want the probability of x and y falling into some region B, I just integrate the joint PDF with respect to B. And this is where things get a little bit tricky in terms of the mechanics of doing the integral, because now I have to think about what this region looks like and how that maps onto the double integral. But in principle, it's the same thing. I just integrate. And finally, if I want the CDF, which we're not really going to use, I just have these two integration variables, u and v, and I integrate up to x and y, and then I go back from the PDF to the CDF. And as in the discrete case, we have marginal, so in this case, marginal PDFs, f of x and f of y, and those are the PDFs for the individual continuous random variables, x and y, right? And the way that we get them is the same thing we were doing before. You just integrate out the variable you don't want, the undesired variable. So if I want the marginal of x, I integrate out with respect to y, and if I want the marginal of y, I integrate out with respect to x. Okay, and remember that having the marginal, so if I reveal the marginals to you, that's not enough information to determine the joint PDF, because it does not tell you how the random variables are coupled or how they interact. Okay, so you need a little bit more information than the marginals. Visually, you can think about the joint PDF as some kind of 3D plot. Okay, so let's take a look at an example here. So I've got my 3D plot, and I've got to watch out that it's not going to be negative, so there are not going to be any negative values here, and that the total volume is 1 because I need normalization. So I need that the total volume instead of the area is 1. So here let's just say that the random variables live in this kind of triangular region, and other than that, they're equally likely to fall anywhere. So the way that I would plot that is just take the xy plane, draw out my triangle on the xy plane, and then elevate it so that I get a volume of 1. And that's what I've done here. Okay, and let's say what I want to get is the marginal with respect to x, then I integrate out with respect to y to get that marginal of x. Okay, so the way this is going to look, if you just stare at this, is that I'm going to have the least mass on the left side and the least mass on the right side, and it's going to kind of jump up, right? So if you look at this triangle, most of the mass on the x-axis is kind of concentrated at the value x equals 2, or kind of in the middle. And that's exactly what you see from this integration or projection. And same thing, if I want to get the marginal of y, I just integrate out x, and I'll see that most of the mass in this case is going to fall all the way at the value 2, and the least is going to be down to 0. And the final thing I want to point out here to you is that the range looked top down is a very useful object. And we're going to see a lot of that in some examples here, right? So what I've done in this bottom right is I've just kind of tilted my view so I'm looking top down, and I no longer see which values are more or less likely. I just see what's possible in the range, and that's a super useful object to have as we try to work out some of these integrals. Okay, so as I mentioned before, for a single random variable, if I want to know the probability of landing in some region, then all I'm going to do is integrate the PDF with respect to that region. Okay, so I just have a single integral, and I just integrate that across A, and then I get the probability of x falling into A. Okay, so we know that. So here's my PDF. My region A is just this little interval. So I figure out what's the area in that interval, and that's it. Okay, that's the probability. So if I have a pair of random variables, it's the same concept. The probability of landing in some region that I'm interested in, right? So let's say I have a region A. I now need to take a double integral. Okay, so I have a probability of xy falling into A, and I'm going to integrate across A the joint PDF fxy. And so what that looks like here, maybe I have this kind of mountain or hill, and then I'm interested in falling in this circle, like what's the probability of falling in this circle A? Then I figure out what's the volume of that. Okay, that's going to be the probability. Okay, so let's do an example. We built up some concepts, let's do a simple example. So here's my joint PDF. It's going to be f of xy, it's going to be a third, okay, x plus y, and the range of it is going to be 0 to 2 for x and 0 to 1 for y, and 0 otherwise. And you can kind of check that this normalizes. I picked all the numbers, so it does. Okay, and the most useful thing I'm going to have is the range. So I'm just plotting for you the range, which is a top-down view of the joint PDF. And this makes sense from those intervals that I'm seeing, which is that I can't have x going outside 0 and 2, and I can't have y going outside 0 and 1. Okay, so here's my first question. What is the probability that the random variable y is going to be greater or larger than the random variable x? Okay, so phrased mathematically, it's just the probability that y is greater than x. And this actually might seem to be a little confusing to you because we haven't technically written down exactly how to do this specific problem. The most important thing to remember is that probability is always about membership in a set. So what does that mean here? It means that there's a particular set, let's call it B, and x and y, when do they fall into that set B? And then once I know that set B, I just integrate the joint PDF with respect to B, and that gives me the probability. So this is where we need to remember that just as in the case with a single random variable, any probability question that I have about a random variable or multiple random variables, it's implicitly asking me about the probability of those random variables belonging to or taking membership in a set, right? So like that's the only thing that you can ask probability questions about, but we might sometimes state those informally. So in this case, I said informally, when is y greater than x? What's the probability of that? But I need to figure out that set. And the way to figure that out is to sketch the range, then try to visualize where that set falls in the range. Then that's going to be the thing that I need to integrate. Okay, so this is the step-by-step process, and I really, really strongly encourage all of you to draw the range before you try to figure out the region. So in this case, I'm drawing this line on the range. This is the y equals x line. So above that line is where y is greater than x. Okay, so this is the region B, and this is actually what I need to integrate. Okay, so the probability that y is greater than x is just the probability that x and y fall into this region, and I need to figure out the limits of this particular integral. Okay, and I plug in the joint PDF. So on the x part, it's from 0 to y, and from the y part, it's from 0 to 1. Okay, so let's take a minute and understand why. Well, the inner integral, I've just chosen it to be x. So you see the dx came first, so the inner integral is from x, And so I start at the left and I go all the way until I hit that line. And at that line, I'm going to put in y, because I can't have the integral in terms of x. I'm integrating out x. But I can put y because that's exactly how that line is defined. So I go up to y. And then for the second integral, the outer integral, I have to get rid of all the variables because I'm integrating out y, and I'm going to be left with no variables. And I just see that it goes from 0 to 1. So this triangle I can get from integrating from 0 to y, and then from 0 to 1. Okay, and now it's just a matter of kind of churning through it, right? So like you could have just left it like that to get full credit, but we're going to just say, oh, it's a sixth x squared plus a third xy. That's the integral with respect to x, and I go from 0 to y. I have dy. Now I'm just going to plug in y here because the 0 is just going to give me 0. So I'm going to have 6y squared plus a third y squared dy, right? And so then when I integrate this whole thing, it'll just end up being a sixth y cubed, right, from 0 to 1. And then I plug in 1 and I get 1/6, okay? So you can work out that integral for yourself. The important thing here is that first, you can kind of look at this picture and think to yourself that, yeah, actually kind of makes sense. This is about 1/6. This is not an equally likely situation. So it's not 1/4 like you might expect from looking at the picture, because the PDF is varying in that range, but still it's kind of less than a half. That kind of makes sense. And the most important thing is just trying to understand how to characterize this set B in terms of the question that I've asked. Okay, so let's do another example. Okay, so we're going to stick with the same setting. All right, and in this setting, we're just going to have, again, the same joint PDF and the same range. And now I'm just going to ask about calculating the probability that y is less than or equal to x. Okay? So we're going to look at two approaches. The easy approach first. So the easy approach is I'm just going to reuse what I did before. Okay? So I reuse the previous calculation, and the previous calculation was something about y being greater than x. Well, here I want y less than or equal to x. That's the probability that xy falls into some region A, and in this case, that region A is just the set of values, right? So it's A, the set of xy values in the range such that y is less than or equal to x. Okay, that's what I want to figure out. And if I draw this, I notice that this green part A is exactly equal to the complement of B. And that makes sense because y being less than or equal to x is the complement of y being greater than x. Okay, so now we can just use the complement property because A complement is equal to B. And so I can just say that the probability that y is less than or equal to x is just 1 minus the probability that y is greater than x. So here I have probability of xy falling into the region A. I can formally say that, well, that's 1 minus the probability that xy falls into the region A complement, and A complement is equal to B, right? So on the next line, I'm just going to replace A complement with B. And I'm just going to recall that on the last slide, what we did is worked out this probability, and we got a sixth. So then it's 1 minus a sixth is 5/6. How could I have gotten this directly? Well, I could just directly integrate across this region A. Okay, so I would get the probability that y is less than or equal to x. That's just integrating across the region A, the joint PDF, with respect to x and then y. And then I would go, so let's figure this out. So I'm going to plug in the joint PDF, and then I have to figure out the integration region. This is the tricky part. Now, if you look at this green shape, you'll notice that it's actually quite convenient for me that I'm integrating with respect to x first, because now I don't need to split the integral. If I integrate with respect to y first, there would be two integrals I need to consider, one between 0 and 1 and one between 1 and 2. There'd be two cases because that line kind of stops after 1. But here I don't need to worry about it, and you'll see that. So I integrate with respect to x first. I have this red line that starts at y and then goes to 2. And then for y, I just go from 0 to 1. And that integrates this green range. Okay, and then I just kind of work through the integral. So again, I have a sixth x squared plus a third xy, and that goes from y to 2, right? And then I'm just going to plug those in, and I'm going to get, let's see, so I'm going to get 4/6 plus 2/3 y, right, minus 1/6 y squared minus 1/3 y squared. Okay, and then I'm going to just try to combine some terms. So this is going to be the integral from 0 to 1 still. I'm going to have 2/3, so I simplify 4/6 plus 2/3 y, that's the same, and I combine the squared terms, I get minus 1/2 y squared dy. And now I'm going to complete this integral, so I'm going to have 2/3 y plus 1/3 y squared minus 1/6 y cubed. I'm going to have that from 0 to 1. Finally, I plug in, I get 2/3 plus 1/3 minus 1/6, and that's 5/6. Same answer, more work, but maybe I had been asked to calculate this thing first, and then I would have gone through the direct path, right? But since I already had calculated the complement, I could use the complement property. Okay, sticking with the same example, so we're just kind of working our way through this. Let's work out the marginal PDFs of x and y. Okay, so I have enough information. I have the joint PDF. From that I know the range. So I just need to figure out what this integral is supposed to look like. So I know I'm supposed to integrate out y by going from minus infinity to infinity. And so what that looks like is I integrate across the range of y. And the range of y in this case is just from 0 to 1. Okay, so I integrate out from y. That's this blue part, so it's just 0 to 1. And I'm left with this integral of x inside its range from 0 to 2. Okay, so I don't want to forget that because x doesn't take values anywhere. It's still staying between 0 and 2. Okay, so now I just have this integral. So I'm working it out that it's 1/3 xy plus 1/6 y squared from 0 to 1. And that's when x is between 0 and 2. And then 0 otherwise. All right, and then if I just plug in 1 for y, I'm going to get 1/3 x plus 1/6 from 0 to 2. Okay, and if you wanted, you could go and check that that satisfies normalization and non-negativity and all of that. Okay, I'm going to do the same thing to get the marginal of y. So I'm going to integrate with respect to x now. So from minus infinity to infinity, I integrate out x with respect from the joint PDF. And then I'm just going to plug in the joint PDF and notice that the range of x is from 0 to 2. Okay, so I put in 0 and 2. And now I'm going to have, just work out this integral. It's 1/6 x squared plus 1/3 xy. And I'm going to just have this going from 0 to 2. Okay, and then finally, I'm just going to plug in, and I'm going to get the PDF of y, the marginal PDF of y. It's 2/3 y plus 2/3. And so notice that now I'm putting in the range of y, which is from 0 to 1. So what's different? So I need to put in this range. I can't forget it, because otherwise I'm leaving out some essential information. And what I did here, which was a little bit of a shortcut, is I left off the range of y when I plugged in the joint PDF. Technically, I should have put it in, just like I put it in for the x case above. I tracked it through every step. But that's annoying to keep writing down. So it's okay to drop it in the middle as long as you don't forget to put it in the end. So that's what I've done here. So I kind of shortened my calculations by skipping the range, knowing that I'm going to remember to put in the end. If you're going to forget, then make sure you write it at every step so that you don't lose track of it. And of course, in both of these cases, I could have just stopped at the integral with the correct limit, so I didn't need to carry this thing all the way through, so maybe that was the only place I needed to write the range to start with. But anyway, if you are trying to carry the integrals all the way through, either write the range at the very end, if you'll remember, or keep track of it the whole way through. Okay, so now we've defined marginal PDFs and we've worked out probabilities. Now let's say that I observe that y is equal to some value, and I want to construct a conditional PDF so that I can work out the probabilities of x falling into some range, given that I know y now has this value. That's going to be the conditional PDF. So the conditional PDF, f of x given y, which takes in the values little x and little y, that's just the joint PDF divided by the marginal PDF of y, whenever that's positive, and otherwise it's 0. Okay, you can define the same thing going in the other direction, so you can have the conditional PDF of y given x, okay? And that's going to be, again, the joint PDF divided by the marginal PDF of x. And this is just a really, really useful object that we're going to see again and again, okay? So this is something that mirrors what we had in the discrete case for the conditional PMF, but now it's defined in terms of the PDF, okay? And technically, if you want to define this formally, you have to kind of go through the joint CDF and the marginal CDF and take limits. And we're not going to do that in this video. You can look it up if you're interested. It's not important. It's just important that you know the form of this and how and when to use it. Okay, so it has the usual PDF properties. So it's basically like a PDF. It just has two variables. So it has non-negativity, right? So no matter what values you plug in, you're never going to get a negative value, right? So both of the conditional PDFs are non-negative. Both of them normalize to 1. Okay, so if you have the conditional of x given y, that normalizes out to 1 if you integrate out x, and y given x normalizes to 1 if you integrate out y. Okay, so notice that I didn't have to integrate out the variable that I conditioned on, right? Because this is a conditional PDF. So I've already restricted myself to this universe, and now probability has kind of collapsed into this universe. There's only one variable to integrate with respect to. Same thing for getting probabilities of intervals, right? So if I want to know that x falls into some region, I just integrate with respect to that region with that single variable, so x or y, depending on which one I want, right? And I also have the usual conditional probability techniques. So if you remember from a while ago, we had the multiplication rule. In this case, the multiplication rule looks like the joint PDF is equal to the conditional PDF times the marginal PDF, okay? So you can kind of see that what the marginal PDF is doing is it's completing the conditional PDF by giving you the thing that you've conditioned on, right? And if you go back to the definition, you'll see that all that does is cancel out the marginal from the denominator of the conditional PDF, leaving you with the joint PDF. We also have the law of total probability. All that's doing is just showing you how to do marginalization if you have one conditional PDF and the other marginal, right? So it's just expanding the joint PDF in a certain way, okay, in marginalization. And finally, Bayes' rule is exactly what we expect it to be. You can flip conditioning by just multiplying and dividing by the appropriate marginals. Okay, so these are the usual techniques we had. I'm just showing you what they mean in terms of conditional PDFs. Okay, let's work out a conditional PDF. Okay, so this is going to be our last example. Back to the same scenario. I'm writing the joint PDF and the marginal PDFs all in one place, and I'm just asking, what are the conditional PDFs? F of x given y and f of y given x. Okay, so the definition of the conditional PDF of x given y is just the joint PDF divided by the marginal PDF of y. Okay, and that's whenever f of y is greater than 0. Okay, so let's just plug in these functions. And the thing to do is just first plug in a third x plus y and divide by 2/3 y plus 2/3. Okay, so that's what I've done. I've plugged in both functions, and I have to remember to also put in the range of x, y. And this comes from the range that I have in the original joint PDF. So the joint PDF, plugging that in is what causes this range to appear here, okay? There's also a range for the marginal of y, but that is a special case of the range of the joint PDF. So I don't need to worry about what happens to the marginal range. I already get it through the joint range. So when I plug in f of x, y, its range automatically captures the condition where the marginal is greater than 0. So I don't need to worry about that. Okay, and then I simplify this. I just kind of multiply through by 3. I get x plus y divided by 2y plus 2. And that's in the range 0 to 2 for x and 0 to 1 for y. Okay, so maybe the one takeaway from this is that instead of worrying about how do I work out when f of y is greater than 0, just remember that when you're working out the conditional PDF, it will always have a statement that is identical to the range statement of the joint PDF. And if you just put that in there, you'll be fine. We'll do the same thing again for the conditional of y given x. I take the joint PDF and I divide by the marginal PDF of x. And I'm going to, again, in the formal definition, I have to check that the marginal of x is greater than 0, but not to worry. All I do is I just plug in the joint PDF, and I'm going to have to remember to plug in its range as well. I have the marginal PDF on the denominator. And so now when I come to put in the range of the joint PDF, which is part of that function, I note that that itself will capture the range where the marginal of x is positive. Okay, so this f of xy is what gives me this range, and I just notice and double check that the 0 to 2 condition for x is already satisfied here. Okay, so, same thing that we had above. So the next thing I can do is I can just simplify. So I just multiply through by, by 6, and I get this slightly simpler fraction. You don't have to do that. I just did it here to clean things up. And the one thing that I really want you to remember is that when you're computing conditional PDFs, the main thing you should be doing in terms of the mechanics is just plug in the range Rxy, okay? And that will take care of the condition that the marginal is greater than 0. Okay, that is the main thing that you need to remember to do, right? And that is it for our intro to pairs of continuous random variables.